All right, section 8.3 is on more things about sets, and we're going to look at the intersection of two sets, the union of two sets, and the complement of a set. So first off, the intersection of two sets is the set of all elements that are in both sets. A way to notate intersection is with this upside down U, A intersect B. And another mathematical word that connects well with intersection is the word and. A intersect B is the set of all elements such that those elements X is in A and X is in B. Now we're going to look at this two ways. Let's consider a Venn diagram. So we have our universe. We have set A. And we have set B. And if we're looking to find the set A intersecting B, we can look at this. Over here, everything in this circle is what is in set A. Everything in this yellow circle is what is in set B. And considering this, all this space out here, this black space out here where nothing is shaded, is what is not in A and not in B. This spot where it's only shaded green is only in A. This spot where it's only shaded yellow is only in B. This spot, this little football shaped thing between these two, where it's shaded yellow and green, is what is in A and in B. And that is the intersection of A and B, this space right here. Another way to look at it is with a finite, with some finite sets, finite examples. So let's consider this example. Let's let the universe be the set of all integers from 1 to 8, including 1 and 8. Let's let set A be the integers from 2 to 5. Let's let set B be the integers from 4 to 7. And now, if we consider the intersection of A and B, that's everything that is in set A and in set B. So if we want to overthink it, we can look and see, okay, A encapsulates these 4 elements. B encapsulates these 4 elements. And what is in A and also in B are the elements 4 and 5. You could have definitely just looked at A, looked at B, and seen what they shared. So A intersect B is the set containing the elements 4 and 5. Another thing we can do with two sets is find their union. So the union of two sets is the set of all elements that are in either set. Now there's an important mathematical concept with this either or thing that's a little different from what we might be used to in English. The word or mathematically means that it can be in one or in the other or both. So the way I like to explain this is, you may have heard someone say you can have cake or pie. And what we mean usually in standard spoken English is, if I say you can have cake or you can have pie, you choose one, not both. Mathematically, if we say you can have cake or pie, you could have cake, you could have pie, or you can have cake and pie. So that's worth noting. In math, in logic, that's what we mean. Alright, the way to notate this is with a regular looking U, U for union. And a word that associates well with union is the word or. The word that associated well with intersection was the word and. So A union B is the set of all elements X such that X is in A or X is in B. Remembering that this word or means it can be in both. Looking at it two ways, if we consider the Venn diagram, we have our universe. We have the set A. We have the set B. And we are trying to find the union of A and B. We can see that this green shade area is everything that's in A. This yellow shade area is everything that's in B. And this unshaded black area around is not in A and not in B. The stuff that's only green is only in A. The stuff that's only in yellow is only in B. The stuff that is in green and yellow is in both A and B. And so what this means is that union is anything that's shaded at all, whether it's just green, just yellow, or both. So A union B is going to be this set that contains everything that is anywhere in either of these two circles. And now our finite example, same sets as we had last time. So if we consider the universe being all integers from 1 to 8, we consider set A as the integers from 2 to 5. And we consider set B as the integers from 4 to 7. Then A union B will be the set that contains anything that's in A or in B or both. So A covered 2 to 5, B covered 4 to 7. So A union B is going to be everything that was covered by one of those two things. The set containing 2, 3, 4, 5, 6, and 7. Now the complement, we're usually going to consider just the complement of a single set. So the complement of a set is the set of all elements in the universe that are not in the original set. Now, we can notate this a few different ways. A way to say this, so intersection was and, union was or, complement is not. So, not A, or the complement of A, is going to be the set of all elements such that those elements are in the universe, and those elements are not in A. Now, we'll look at it two ways again. So if we have our universe, and we have a set A, and I'm going to put in a set B just because, well, I'll talk about why it doesn't really matter shortly. Put in set B. If I want to find what is in not A, or the complement of A, I know that this green shaded region is what is in A. So everything that was not shaded in that green shaded region is in the complement of A. So that would include everything down here and everything around here. So it's all the space inside this rectangle that's not in this A circle. Now notice it didn't matter where B was. There's nothing to do with B here. So B could have been inside of A, B could have been completely disjoint from A. It didn't matter. Only thing that mattered was where the universe, what was in the universe, and what was in A. So we'll consider the same example we saw before. If my universe is the set of all integers from 1 to 8, if set A is the set of all integers from 2 to 5, set B is the set of all integers from 4 to 7, then the complement of A is going to be the set of all values in U that are not in A. And looking at this, 2, 3, 4, and 5 are in A. So the ones that are not in A will be everything else. 1, 6, 7, and 8. Okay, the last thing we're going to do, or the last two slides, is we're going to look at a few examples to see how they look. So we're going to combine intersections, unions, complements. In today's lesson, we're only going to consider a universe set and at most 2 other sets. Tomorrow we'll consider 3 or more sets in there. So we'll still keep it relatively simple, but let's consider this. So first, let's look at some Venn diagram examples, and let's consider the complement of A intersect B. So I'll draw a universe. I will make set A. I will make set B. And now let's look at this. So we just saw what the complement of A looks like. That is everything that's not in this A circle. It's going to get a little bit sloppy, so bear with me while I do this shading. I'll clean it up before the final answer here. So we have all this space. That's the complement of A. B, just regular old B, is everything that's inside this B circle. So that is this. And intersect is everywhere where these two sets meet up, where it covers both of them. So what's in green is A. Oh, sorry. A prime, the complement of A. What's in B, or what's in yellow is in B. What's in the intersection is where it is both. So where it's both is most of this yellow circle, but not this football-shaped area that just has the yellow. So the intersection of the complement of A and B is this section of the Venn diagram right here. Another example, if we consider the complement of the union of A and B, I draw universe, draw a set for A, and draw a set for B. So looking at this, remembering what we had before, the union of A and B is everything in A or in B or both, which was this area right here. Going all the way out to this circle. Okay, everything that's in both of these combined. The complement of that is everything else, this black area around both of these circles that's still inside of the rectangle. So the complement of the union of A and B is going to be all of this area. Everything going around here and around here, but not in either of the circles. So those are two examples combining things as Venn diagrams. Now, let's consider a few examples with finite sets. So I'll give three different sets, easily defined with three different sets. Let's let the universe be the set of all integers between 1 and 9 this time. So x such that 1 is less than or equal to x less than or equal to 9, and x is an element of the integers. Let's let A, and I'll use the color scheme again. Let's let A be the set of odd integers in there, so 1, 3, 5, 7, and 9. And let's let B be the set of prime integers between 1 and 9. So B is going to be the set containing 2, 3, 5, and 7. Now, before I actually do the work here, it may be easier for us to consider this if I write U out explicitly instead of using this format. So I'll go ahead and do that first. So the universe written out is going to be 1, 2, 3, 4, 5, 6, 7, 8, and 9. If you ever have a case in a problem where you can't quite figure out what is and is not, if you list things out, as long as they're not too many elements, it can help you see what you're looking for. So, a few examples. First, let's consider the complement of the intersection of A and B. So, first off, the intersection of A and B is everything that they share. So they share 3, 5, and 7. Now, the complement of that is everything else. So if they share 3, 5, and 7, the complement is going to be everything that's not that. So if I take out 3, 5, and 7, what's left over in the universe will be this answer. So let's get rid of all those markings. The answer here should be the set containing 1, 2, not 3, 4, not 5, 6, not 7, 8, and 9. Next, if I consider the complement of A intersect the complement of B, that's going to be everything that is shared between what is not in A and not in B. So in here, let me list that off. What is not in A is going to be, let's see, it has 1, it does not have 2, it has 3, it does not have 4, it has 5 but not 6, it has 7 but not 8, it already has 9. And let's consider the complement of B as well. So B does not have 1, so its complement will, but it does have 2 and 3. B does not have 4, does have 5, does not have 6, does have 7, but does not have 8 or 9. So the intersection between the complement of A and complement of B is what these two have in common, which is 4, 6, and 8. Now, something that's worth noticing, these are not the same. If you have the intersection of A and B and take its complement, it's not the same as the complement of A intersect the complement of B. But let's look at the complement of A union the complement of B. So what is in A or in, the complement of A or the complement of B or in both. So in there, the complement of B has the element 1, the complement of A has the element 2, they both have the element 4, they both have the element 6, they both have the element 8, and the complement of B has the element 9. Now, we're not going to focus on this, but this is a rule. The complement of A intersect B is the union of the complement of A and B. And if I had the complement of A union B, you might be wondering, and this will be as an exercise tonight, whether that is actually the same as the intersection of the complements of A and B.